We've noted already that the equilibrium constant is itself a function of temperature, but not of anything else. So it is a function of temperature. Now, I've written down here our thermodynamic expression for the equilibrium constant, and it's very clear that temperature is a part of that expression. So is that the temperature dependence that we mean? In fact, the temperature dependence is the more important temperature dependence for our sake is coming from the temperature dependence of the delta G term in this. And that's the part that we want to get a handle on. So what I want to do is basically rewrite our equation in such a way that we can determine something about the temperature dependence of K by knowing something about the temperature dependence of G. So in other words, where I want to begin our examination of this is to rewrite this equation something like this. So we know that delta G is equal to minus RT log of K, and I'm going to indicate explicitly that K is a function of temperature. Now, what I want to do to develop this equation is I want to first divide both sides by the temperature. So, in other words, I'm going to have delta R G0 divided by T is equal to negative R log of the equilibrium constant. Now, the reason I'm doing this is because I've already seen what happens if I take the temperature derivative of this quantity over here. And I want to remind you what that looks like. If I take the derivative of delta G0 over T, so let's, with respect to temperature, and we're going to make all this at constant pressure, what I have is that this is equal to negative delta H0 over T squared. You recognize this equation. It's basically the Gibbs-Helmholtz equation. And the Gibbs-Helmholtz equation gives us a way of getting a handle on the temperature dependence of the equilibrium constant. Let's see how that works. So if I know that this is true, if I were to take the take the derivative with respect to temperature of this equation here, I would get this on the left-hand side, and I would get the temperature derivative of this term on the right-hand side. So in other words, I would have something like the temperature derivative of this thing is negative R times the temperature derivative of log K of T over dt. And now instead of putting this in the middle, I'm just going to give what it's equal to from the Gibbs-Helmholtz equation, minus delta H over T squared. All right, now this I can unpack. First of all, I can make both of these pluses, and then I can move this dt over to the other side and essentially have an equation that looks something like this. D of log K is equal to delta H, and I'm going to divide by R, so delta H0 over R dt over T squared. So all I've done is rewrite this equation over here a little bit more organized fashion. Now what I want to do is I want to take this equation and integrate it. Okay, so I'm going to integrate from a state 1 to a state 2, which will be characterized by the temperatures T1 and T2. And let's just say for the sake of argument that T2 is greater than T1, so we're integrating up to a higher temperature. All right, so now what I would be integrating over here, T1, T2, is this quantity. Now I'm going to do something that we've done many times before. I'm going to make the supposition that this temperature range, or at least within this temperature range, this enthalpy change doesn't change very much. So in fact what we can do is take it out of the integrand, and I'll end up with the following sort of equation. So when I integrate this, I'm just going to get log of the equilibrium constant evaluated from T1 to T2. And on the other side, I'm going to get delta H0 over R, and then the integral of this thing is negative 1 over T, again integrated from T1 to T2. Okay, well I can in turn write that as negative delta H0 of the reaction divided by the gas constant times 1 over T2 minus 1 over T1. All right, and on this side I'll have simply the log of K of T2 minus the log of K of T1, which I can simply write as the log of the ratio K of T2 divided by K of T1. And what I've written here, and I'll put a box around it to make it special, what I've written here is something called the Van 't Hoff equation. And Van Hoff was a chemist in the late 1800s and early 1900s who did a lot of work in thermodynamics and especially involving chemical equations and chemical reactions. All right, but this Van Hoff equation now is very directly telling us how the equilibrium constant changes as a function of temperature. So now we know how it varies as a function of temperature, and we can actually quantify that. Now, I want to rewrite this equation a little bit by well, I'm going to redefine some of these variables just so that it makes it clear. But if I were to define this variable here as equal to y2 and this variable here is equal to y1, then I could define this variable here as x1 and this one as x2. Okay, I think you see where I'm going. I can make a plot of y versus x, but really what I'm plotting in this plot is something that looks like this. Okay, so here's my plot. X is equal to 1 over t, so I'm plotting on my x-axis 1 over t. Y is equal to log of the equilibrium constant, so I'm plotting log of the equilibrium constant. Now, what this is telling me is y2 minus y1 is equal to some constant times x2 minus x1. Well, that's just the equation of a line. All right, since it's in a line, then I should expect if I make a bunch of measurements at different temperatures, I'm going to end up with something that looks roughly like a line going through here. And in fact, the slope of this line is going to be given by this. That's the slope. So in fact, this gives us an interesting way to measure the heat of a reaction. All right, by simply measuring the equilibrium constant at several different temperatures and plotting its equilibrium constant versus 1 over temperature, we can get a line that should be a slope, it should be a line, and its slope is something that tells us what the delta H is. All right, now let's look at this a little bit because I've drawn this as a negative sloped line. Is that always going to be the case? Well, let's take a look at delta HR and what it means. Okay, so let's suppose I have delta HR is less than 0. Okay, what does that mean physically? Well, that means we have an exothermic reaction. We have a reaction that is giving up heat to its surroundings, so the system is losing heat. And that would translate to something where the slope, since the slope is equal to the negative of delta H, if delta H is negative, then the slope will be positive. So I'll emphasize that over here. Okay, so the slope is positive, not negative. So we can have situations in which we have a positive slope, and that would be anytime we have an exothermic reaction. Now the case that I've drawn here would correspond to delta H being greater than 0, which is an endothermic reaction. And so in this case, as we've seen, the slope is less than 0 or negative. All right, and this is going to correspond to a endothermic, or a case where we have to absorb heat from the surroundings for the reaction to happen. Now, I want to point something out, and that is, since we're graphing versus 1 over temperature, we need to be careful about how we analyze this. All right, when I look at the temperatures along the scale, this end is large temperature, and this end over here is small temperature. So in effect, for the endothermic case, I've got K getting smaller as T is getting smaller, and K is getting larger at this end as T is getting larger. So in this case, in the case of endothermic reactions, K increases with temperature. All right, I hope you can see that the opposite will be true for exothermic reactions. In the case of an exothermic reaction, as we increase the temperature, we will actually decrease the equilibrium constant. So we will inhibit the formation of products in that case. This is a very important conclusion to reach because it tells us something about the relationship of those very fundamental quantities, heats of reaction, and where we can expect the equilibrium of those reactions to lie, whether it is going to favor products or favor reactants as temperature changes.